elementary reactions and catalysis. Hydrogen is used as a rocket fuel. Hydrogen is also used in some batteries that are being developed. The problem is the hydrogen is really explosive. Right now, NASA does have a hydrogen gas sensor, that will change color or something, will indicate the presence of hydrogen gas, but it's electrically based. NASA needs something that's not electrically based, because if it's electrically based, that sensor depends on electricity to run. So that means that it's powered. It could be, if there's hydrogen gas present and there's a short circuit, the sensor itself could cause the explosion. So not a good idea. So a non-electrically based sensor is needed. So Dr. Smith's hydrogen gas sensor to the rescue. I spent a couple summers at a NASA research facility, and here's one of the things that I was working on. Okay, here's hydrogen gas, and remember, hydrogen gas is explosive, and it's also lighter than air. So I'm going to keep this inverted, pop it open, just to help you remind you that hydrogen is explosive. I don't know if you heard that. Not very much. Okay. Now, this container has hydrogen gas, and here is my sensor. Okay. Right now it looks kind of greenish, dark greenish, grayish color. Okay. In the presence of hydrogen, it's going to change color on us. So I'm going to keep it inverted like this. Transfer the hydrogen into my sensor by flipping it upside down. See it turning darker blue? It's turning darker blue. So that's an example of a catalyst reaction, this hydrogen sensor. I can't tell you what the catalyst is. It's a super secret research project. It has issues. Otherwise, I'd be a millionaire. But the point is that hydrogen gas, in the presence of the sensor, when it's regenerated, when it's green, it turns the sensor blue. Okay? Without this catalyst, this hump would be much, much higher without that catalyst. Okay? So what is the difference between a homogeneous and a heterogeneous catalyst? Well, homogeneous means same throughout. So that means a catalyst is the same phase. Same phase as the reactant. In my case here, my reactant is hydrogen gas. It's a solid, so this would be a heterogeneous example of a catalyst. Elementary reactions. What is the difference between an elementary reaction and a reaction mechanism? It was a while back, but they were finding that it was really easy to get a sunburn over Antarctica. There wasn't any ozone, and this ozone hole was getting larger and larger and larger over Antarctica. And they found the reason was chlorofluorocarbons. And here is the reaction mechanism that causes it to happen. Okay? So our loss of ozone was due to chlorofluorocarbons, and a lot of research went into this, seeing how there's step 1, step 2, step 3, step 4, multiple steps in this overall reaction. So this is a reaction mechanism. Each of these individual steps is an elementary reaction. Okay, but the whole thing is a reaction mechanism. If the following elementary reactions occur in a known reaction mechanism, what's the overall reaction? So everything so far in general chemistry has always been these overall reactions. We've never dealt with the steps. So here, right, those would cancel. We'd end up with 2 A's and a B on the reactant side form D on the product side. So that would be our overall reaction. What is the molecularity of each elementary reaction in the above mechanism? So just some terminology we need to get used to. That's just the number of reactant molecules. Okay, for each step. So the molecularity for this, how many reactant molecules are there? There's just 2. Here, there's 2. So the molecularity of each of those steps is 2, because there's 2 reactant molecules in each step. Write rate equations for elementary reactions. You remember writing rate laws before was a lot of work, but for an elementary reaction and one step in a mechanism, oh, they're nice. So rate equals K. So does this sound familiar so far? And then you write the concentration of the reactant, in this case it's A, and just raise it to the stoichiometric coefficient. And we're done. For B, again, rate equals K, the concentration of each reactant raised to their stoichiometric powers, and we are done. D to the 1, C to the 1. Right? You don't have to write the 1s if you don't want to. Writing overall rate equations, rate laws for mechanisms. Okay, so here they give us a reaction mechanism. So that means they give us all the steps, and they tell us one of them is slow. That's often known as the rate determining step. The slowest step is the rate determining step, because everything else is fast. So pretty much we just write the rate law for this step, and we have the rate law for the entire mechanism, because this is what slows everything down. So rate equals K, concentration of A, concentration of B, each raised to the 1 power. What is the molecularity of each of the following reactions? Again, just count up the number of reactant molecules and you're done. 3, 2, 2, and 1. Write a rate equation showing the dependence of rate on the reactant concentrations for each of the following reactions. So these are our elementary reactions. So again, we just write it of our regular form. Rate equals K, concentration of each reactant raised to their stoichiometric power. The reaction of thioacetamide with water is shown by this equation. And here's the reaction is given by this rate law. So they're giving us the rate law. Consider 1 liter of solution that's 0.2 molar in thioacetamide and 0.15 molar in hydrochloric acid at 25 degrees Celsius. For each of the changes listed below, state whether the rate of the reaction increases, decreases, or remains the same, and say why. Okay. Do you remember that guy? Le Chatelier, right? His principle is going to really apply here in some of these, I'm sure. Okay. A 4-gram sample of NaOH is added to the solution. Okay. They told us the rate law, so they're interested in the rate of the reaction, not so much in equilibrium, which is what Le Chatelier was talking about. So it's generally the same idea, but we need to look at the rate law. Okay, so we don't look at the equation, we look at the rate law and see what the effect is of each of these on the rate law. Okay, so I'm adding NaOH. Would that have any effect on anything in my rate law? Okay, the only way I affect K is to change the temperature, so that's not going to do anything. Adding NaOH. Will adding NaOH affect either of these? The answer is yes. Which one? We hardly ever write H3O plus, right? We always write, that's the hydronium ion, by the way. We always write H plus. And remember, H plus OH minus, always, 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 big time, water. There's a little tiny backwards reaction, but you can't hardly even see it, okay? So we form water. So by adding hydroxide, right, we are removing H3O plus. So if we're removing H3O plus, this concentration has to go down, right? We're removing it. So if that concentration goes down, the rate has to go down. So the rate decreases. Let's clean this up. 500 mils of water is added to the solution. What will be the effect on the rate? Will the rate increase, decrease, or remain the same, and why? So we look at our rate law. What effect would adding water do? Okay, how about on the rate constant? Only way to change it is to K. Well, that's not water, that's H plus. And this isn't water. Right, that's thioacetamide, but they're in brackets. So these are concentrations. These are concentrations. Right? Isn't that what those brackets mean? What is the solvent? Is the solvent water? Look at the reaction. The reaction says AQ. What did AQ mean? AQ meant aqueous. Solvent is water. We're adding solvent. By adding water, we are making all the concentrations more dilute. Right? So the concentrations are going down. We're decreasing the concentrations. We're adding solvents, so the concentration is going down. They're being diluted. A lot, too. 500 mils of water, that's a lot. So if we're making things less concentrated, these numbers are going to be smaller. So the rate has to go down. So the rate also decreases. Okay. A catalyst is added to the solution. Well, catalysts always what? They always increase, right? They lower that energy of activation, they increase the rate. Increase the rate. Because the energy of activation is lowered. I guess that's where the K, that's another way to change K. Right? Not only with temperature, but also with an energy of activation. If you have a catalyst, that's going to make K a lot bigger and speed up the rate of the reaction. The reaction is carried out at 15 degrees instead of 25 degrees. Okay? So we're cooling things down. So if things are moving slower, right? They have less energy. Less energy available at lower temperatures, right? They're moving around slower, right? It lowers the rate at lower temperatures. Draw a potential energy diagram for an uncatalyzed exothermic reaction. Then on the same diagram, indicate the change that results on the addition of a catalyst. Discuss the role of a catalyst in changing the rate of the reaction. Okay, potential energy diagrams. Remember those from the last video? What we did is we had two axes, and I think we wrote energy here. We should have wrote potential energy. Okay. And then we have reaction coordinate. Okay. And we want an exothermic reaction. So you remember how that looked? Start high, end up low. So the reactants are way up here, and the products are way down here. Then there had to be an energy of activation between the two. Okay? And then we had our, remember how to illustrate all these things? We had our enthalpy. It's not asking for this, but I'm on a roll. We had our enthalpy, and then we had our energy of activation, or EA. Okay. Okay, so that would be uncatalyzed. Okay, I'm going to change the color to red here and make it catalyzed. Red is catalyzed. Okay, so how is that curve going to change? Everything is the same, but what? That energy of activation. It just gets lowered. I have a new energy of activation. All right? So to discuss it, all right, catalyst lowers the energy of activation, right? So the rate constant grows, it increases, and the rate increases. So we can't influence the energy of these reactants and products. They are what they are. But we can lower the energy hump, the hurdle that they have to get over to get converted into products. That's what a catalyst does.